Well, I think you have to give me option, right? Yeah, you're able to hear? Okay. I think there's some triple E or something. I think I've given now. Okay. Yeah. So I think we can start. Okay. Yeah.
So we have given you co-host. You can start the session now.
So can I start? Hello? Hello? Yeah, are you able to hear me? Hello?
Yes,
Hello?
sir. We are able to hear you.
Yeah, I think you can start maybe the introduction and then we can I'll proceed, or do you want me to start right away?
Yes, sir. We can start the session, sir.
Okay, fine.
I extend a warm welcome for all the participants of today's session of AICTE sponsored faculty development program in machine learning, in computer vision and video processing. I extended a warm welcome for today's speaker, Dr. Suresh Sundaram, sir. Dr. Suresh Sundaram, Associate Professor at IIT Guwahati. Dr. Suresh Sundaram received his PhD from Indian Institute of Science, Bangalore. His research interests include pattern recognition, image, video processing, and computer vision. He has published 39 research papers in reputed journals. He has organized several international conferences and workshops. He has guided 3 PhD students and also handled 3 research projects. Now I request Dr. Sundaram sir to take over the session.
Okay, thank you very much for the introduction.
Thank you, sir.
Okay, so I think we will just start right away. So the topic for today is okay. So yeah, so the topics for today's discussion is why is it turning up the post attendee Zoom? Is there some problem or? Yeah, okay, yes, I got it. So let me share the slides first, okay, and then we can start. Okay, so today I'll be covering on Bayesian decision theory, okay, for computer vision, okay, and so what we will do is that we will start right away with what Bayesian decision theory is about, okay, and then how to do classification. All right, so let me share the screen first. I think I'm going to share the so are you able to see the screen now?
Not yet, sir.
Not yet, no? So let me.
Not yet.
I think this is the desktop. Yeah, able to see now? Bayesian decision making. Hello?
Yes, sir. We are able to see now.
Sir, yes, sir, visible, sir.
Okay, fine. Okay, so today I will be talking about this Bayesian decision theory. See, computer vision is a very big field. Okay, it encompasses image recognition, machine learning, and so on. But whatever I'm covering today is the basics of Bayesian decision making, and it's applicable to video processing computation. So, for example, Bayesian decision making for identification purposes. Okay, supposing I want to identify, let's say, apples and oranges. Okay, so Bayesian as one of the topic. It has very vast applications. In fact, these days, many of you would have been aware of CNN architectures, right? So they're all built on this Bayesian decision-making principle only. Of course, that's a different way paradigm altogether, but the idea is simple, right? You know, class that gives you the maximum posterior probability. Okay, so that is the main idea. So what we will do is we will quickly go through some of these slides, okay, and then we will continue. So one thing is that, okay, the decision-making process, okay, using the Bayes decision theory is going to be based on probabilistic inferences. Okay, so we are going to use probability principles to actually apply the classifier. So all of you are familiar with Bayes rule, right? Am I audible? No problem, right? Hello? Hello?
Perfect, sir. It's audible, sir.
Oh, okay, fine. So we will be applying this Bayes rule, okay, to actually design our classifier, okay. And whatever I'm covering today, okay, the applications to computer vision are, supposing I want to do object detection, okay, I want to detect whether a person's face is there or not, okay? Or whether I want to recognize an object, okay, I want to recognize a chair from a table, okay, let's say breed of animals, okay, so you understand, right? Or I have seen 5 mountains, okay, I want to identify. So these are all computer vision based applications, okay. So what we are going to cover today is the basics of Bayesian decision making, okay, and it is going to be based on probability principles, okay. So I'm just giving you these applications because they are very important, okay. So for example, if you have application, right, so I want to check, okay, whether a given object is what it is or whether it is something else, okay. So I also want to check, I also wanted to use for segmentation and so on, okay. So what I'm trying to tell today is that, okay, this basic principle will be used throughout in any machine learning algorithm, be it in deep learning or maybe even in the conventional learning, okay, of handcrafted features, okay, this basic ideas will move forward there. So what we will do today is that we will learn how to do Bayesian decision theory, okay, and we will assume that, okay, the model is generative, okay. What do I mean by that? It means that, okay, the training samples, okay, which are there, okay, they're all assumed to come from a probability, okay. So example, I can actually say that if I have 2 classes, okay, say omega 1 and omega 2, and the 2 classes can be 2 objects that you want to recognize, okay, I can probably say that the distribution of omega 1 follows a Gaussian distribution and the distribution of omega 2 follows a uniform distribution, or it can be that both the classes have the same distribution but different parameters. Like you may have a Gaussian with, say, a mean 0 and some variance, and you may have another Gaussian with mean 1 and standard deviation as 2 or something, okay, for the other class. So what we are going to assume is you're going to assume there's an underlying distribution. Okay, so that is why these are known as generative models. Okay. So now we are also going to give labels to the class. Okay. So for example, we are going to label the classes. Okay. So the training sample. So this is what is known as supervised learning. Okay. So what does supervised learning say? Supervised learning says that we will have training examples, but the training examples are labeled. Okay. So you will say that fine. If I have an object, okay, say one object, let's say, is an apple. Okay. So I will label all the samples of apple as omega-1, and let's say the other fruit is oranges. I want to identify between apples and oranges. Okay. All the samples of oranges will be marked as omega-2. Okay. So there will be a label given instances of a particular class. Okay. So now what I'm going to cover is a conventional decision-making problem. I'm going to start with, this is an example from the textbook, Duda, Hart and Stock. Okay. So I've just directly taken this example from there. So there the problem is you want to identify two types of fish. Okay. One is sea bass and other one is salmon. Okay. So this is a typical computer vision problem. Okay, because I want to identify the two types of fish, and the fish are actually going through a conveyor belt. Okay, so I want to identify the type of fish. Okay, and this is a two-class or a category problem. Okay, so what is the first step? We will have to assign labels to the classes. So let omega-1 be a sample, okay, of salmon, and let omega-2 be a sample of sea bass. Okay. Now, if I'm going to say that the salmon is going to occur more likely than sea bass, and if I'm just going to use this for making my decision, okay, this is known as prior. Okay, this is known as prior. Okay, so the prior knowledge, okay, that, okay, on an average, the salmon occurs more likely than a sea bass. Okay. So that means, mathematically speaking, the prior is denoted by P because it's a probability. Okay. So I will say P of omega-1 and P of omega-2. Okay. And since salmon occurs more likely than sea bass, P of omega-1, which is the probability of salmon, is greater than probability of sea bass. Okay. So let me say that I want to choose omega-1 whenever P of omega-1 is greater than P of omega-2. Okay, so let me say this is my decision making. That is, I choose the class sample to be of salmon because salmon occurs more frequently or more likely than sea bass. Okay, so there happens to be an issue in this type of formulation. Okay, so the issue is that if you rely only on the prior, okay, then your decision is going to be flawed. Okay. So what do I mean by that? Okay. It means that every time the salmon is going to be chosen. Okay. The salmon is going to be chosen. Why? Because its probability is higher than the probability of the sea bass. Okay. So please ask doubts if something is not clear. Okay. So I would like to proceed on, but is there any doubts so far? Anybody has any doubts in whatever I said? So if you rely only on the prior, your decision is going to be flawed because you are going to always choose one class over the other class every time. Okay. So does it mean to say that the sea bass will not occur at all? Okay, the sea bass will occur, but it will always get classified as salmon. Why? Because the probability of the salmon is greater than the probability of sea bass. Okay, right? So this is a flawed decision. Okay, so rather what we will do, so let's just give an example here. The salmon will always be favored and assigned to the test fish. Okay, and such a practice will not work in practice. Okay, So if you depend only on the prior probability for making decisions, it's not a good idea. Okay. So now, yes, so there is a small doubt. Let me check on the chat box. Okay, so I'm just going to come to that. How to find the underlying probability density of data set. We'll come to that. Okay, very soon. So now, let me just tell you how to get the priors first. So the priors are obtained by a frequentist approach. Okay. So let's, for example, say that you have 8,000 fish samples. 6,000 was salmon and 2,000 are sea bass. So I will assign 0.75, okay, to be the prior probability of salmon because 6,000 salmon were there, and 0.25, 2,000 by 8,000 as a probability of sea bass. Okay. All right. So now I would like to move on to, yes. So what is the question that is being asked? Okay. So how do you get this underlying distribution? Okay. So we actually, when we do a machine learning approach for anything, for any computer vision, the first step that we do is you take an image, okay, or whatever, and then you kind of zone on to the object of interest, okay. You describe the region that you have selected by what are known as features, okay. So, and once you have some features, okay, you will have to actually develop a classifier. Okay. So we assume now that the features that you choose should be discriminative, correct? So if you have a sea bass and a salmon, so you have two objects or two types of fish that you want to classify. Okay. You have to extract some features that will discriminate between sea bass and salmon. Okay. So some of the features that can be used are length, let us say width, okay, length of a fish, width of a fish, then color, okay, then you can have texture, okay. Now these are all, some of them can be derived, okay. Let us say if you have an object like an image of a sea bass and an image of a salmon, you can actually do some image processing techniques such as morphology and so on and measure the length and the width, okay. Then you can look at the RGB, okay, and then channels, or you can convert them to the appropriate color spaces so that you can discriminate the color information. Okay. Then lifespan is probably given to you by the biologist or so on. So, but texture, okay, you can actually use image processing techniques to actually develop some features, okay, that can be used for texture. So some of the features that can use design texture are Gabor filters, okay. Then we can use spike moments, humans, and so on. Okay. So you're going to, in the end of the day, you're going to derive some features. Okay. That is going to describe the sea bass or a salmon. And the idea is to look for discriminative features. Now, these days, okay, we don't need to design these features handcrafted because as most of you are aware, okay, that there is an area which is known as deep learning, okay, where you talk about convolutional neural nets and recurrent neural networks. There are different architectures available, okay, that will help you to get rid of these handcrafted features, and the feature learning is done automatically, okay, end to end, okay, with the classification and end to do the recognition, okay. But so whatever be the case, in the end you have to do a classification, okay. So for that you can use a Bayesian decision theory, okay, or you can use a feed-forward neural network or so on. But what I'm going to cover today is the basic philosophy of Bayesian decision theory. So let us, for the time being, assume that the features are provided to us, okay, and you have some handcrafted features, okay, fine. So now let us assume that you have D features, okay, and now I'm going to say that each of these features, okay, describing a fish are going to be represented by a D-dimensional feature vector. So if you have D features, you can stack the features in a column vector, okay, and that is of D dimensions, okay. Next. So now this is where I was coming to. So for every class or category of fish, okay, we are going to associate the D features, okay. So the D features that you have, you're going to associate them to come from a probability distribution function. Okay. And this distribution function, which is the PDF, okay, will be referred to as a class conditional density. So let me give you an example here. Okay. So let us say, and this one, so let us say I have two classes, omega 1 and omega 2. Okay. So I can probably say that a particular feature of the type of fish in this example, let's say length. Okay. If I plot the histogram or the distribution of the length for omega 1, it is a curve something like this. And if I plot the distribution of omega 2, okay, for that feature, it is something like this. So essentially, I'm assuming that there is a distribution associated to each of the classes. Okay. There is a distribution associated with each of the classes, and it is conditioned on a class. Okay. It is conditioned on a class. So I would say that this curve, okay, is say P of X given omega 1, because it's the probability of a density of a feature conditioned on omega 1. And this curve, which I'm showing here, is P of X given omega 2. Okay. So it is like this, right? I mean, we can actually make statements like, okay, the if you take the class omega 1, okay, so we can say that the length of the samples, okay, of omega 1, they follow some distribution. Now, how is that distribution decided? Okay, that could be one of your questions. Now, that is decided either through prior knowledge or it is mostly done through measurements. Okay, so you take multiple samples of that particular fish in this example, measure that feature, okay, and you plot a histogram, and in a continuous version of the histogram will be nothing but the probability density function. Okay, so that is how we actually get it. Okay, so for example, right, I'll give you another example here. Supposing you want to check, okay, the two fruits, let's say apples and oranges. Okay, so apple is red in color, orange is orange in color. So I can probably talk about some red measurement, orange measurement, green measurement, and so on. Okay, and then I can get a vector, and I will see that distributions of apples, okay, their redness value will differ from the distribution of redness value for an orange. Okay, because an orange is different from an apple. Okay, so how do you get distribution? They are conditioned in the class, and they are obtained by considering a continuous form of the histogram. Okay, so that is the way it's done. All right. So we assume that the features are continuous. Okay, and as I said, for a set of d-dimensional feature, d feature describing the fish, we are not going to talk about one-dimensional distribution. Rather, we will talk about a d-dimensional probability, class conditional density, or a distribution. Okay. So now, let us, for the time being, to begin with, okay, improve our decision process by incorporating a single feature, X. So that means the feature is one dimension. Okay, we are going to make the decision-making process by using only one dimension or one particular feature. And later on, like very soon, we will extend this framework for d-dimensional features. Okay, and now we are considering only two classes, right? We'll also extend this process for classes greater than 2, number of classes greater than 2. So as I said, this is the idea of the class conditional density. Okay, so for a given feature, okay, this is the kind of density that you will obtain for a given class omega 1, and this is the density that you'll obtain for another class omega 2. Okay, so all of you should be familiar with Bayes' theorem. Okay, so Bayes' theorem says that P of omega j given x, okay, is P of x given omega j into probability of omega j divided by P of x. Okay, and when P of x is called the evidence, P of x given omega j is called the likelihood, or the likelihood is nothing but the class conditional density value, okay, at a given value of x for a class omega j, and probability of omega j is the prior, okay, or the prior probability of getting omega j, okay. So if you multiply the likelihood into prior and normalize it by the evidence, which is P of x, you get what is known as a posterior probability. Please remember that P of x given omega j is a probability density function. Okay, don't confuse it with probability. Okay, so all of you know what a probability density function is if you have taken a course on random variables. Okay. Probability density function, okay, it is related to the probability in a sense that the area under the PDF will give the probability in that interval. Okay. So it is like population density, right? What is population density? It is the population per unit area. So likewise, you can consider probability density to be a probability measurement per unit area. So if you multiply by the area of the curve, right, you will get a probability value. Okay. So what we are trying to do is we are considering the class conditional density value at a particular x or a given class omega j. So let me just explain here. If I, for a given value of 13, let us say, if I want to read out probability of x given omega 1, I will have to read out this value. Okay. Whereas for the same point, okay, P of x given omega 2 would be this value. Okay. I hope it's clear in this illustration. So we are going to read out the probability density value or the likelihood, what we call, at a given x. Okay. And the evidence is what is known as probability of P of x given omega j, probability of omega j, the density, that is j equal to 1 to 2. So now, what can we say about a decision? We get two posterior probabilities for the case of two classes, probability of omega 1 given x and probability of omega 2 given x. And we need to choose that class, okay, whose posterior probability is the greatest. Okay. So what do I mean by that? Okay. So that means, let's say for a given value of 12, x is equal to 12. Okay. If the, assuming the probability of omega j given x is a curve, something like this. Please note that at any given x, okay, the probability of choosing omega 1 and the probability of choosing the class omega 2 for that value of x, which is nothing but the posterior probability, will sum up to 1. Okay. So you can see that here. So let us take a value, say 13. Okay. If you read out probability of omega 2 given x, it is around 0.2. But if I read probability of omega given x, it is close to 0.8. Okay. So 0.2 plus 0.8 is equal to 1. Likewise, any value I take, okay, if I take a value, let's say 10, right? Probability of omega 1 given x is some value close to 0.6, and probability of omega 2 given x is a value just above 0.4. So that these two, when they add, that is equal to 1. Remember that the axiom probability will hold good here. That is, the sum of probabilities of events, okay, will be equal to 1, and the probabilities will always be greater than 0. So all those axioms you should remember. Okay. So what we are trying to say now is that for a given x, okay, I can compute this equation. Okay. I can take the class conditional density value or the likelihood, multiply with the prior, divide by the evidence. I'll get a posterior probability for that x for each of the classes, and I will choose that class, okay, whose posterior probability is the greatest. Okay. So if I choose, let's say if I'm taking 13 as the value of the length, okay, x in this case, I will actually be choosing omega 1 class over omega 2. Why? Because probability of omega 1 given x is greater than probability of omega 2 given x. Okay. So what are we trying to say now? The decision is based on the posterior probabilities as follows. So if you have a test data x on observation, and if you see that the posterior probability of omega 1 class is greater than omega 2 class, or rather probability of omega 1 given x is greater than probability of omega 2 given x, I will say that the true state of nature or the classifier should predict class omega 1. Okay. On the other hand, if probability of omega given x is less than probability of omega 2 given x, okay, I will say that the true state of nature is omega 2. Okay. Now, whatever decision you make, okay, that is the probability of correct decision. Now, there's always an error that will turn up. So that error, condition error will be probability of error given x, will be probability of omega given x if you decide omega 2, because omega 2 will be the probability of choosing omega 2. So the error will turn up if you choose omega 1 instead. Okay. So it is probability of omega 1 given x, and vice versa. Probability of error given x can be probability of omega given x if we decide on the class omega 1. I'll give you more details of this as we proceed on. So what the posterior probability would be the probability of correct decision. Okay, it's presumed to be a probability of correct decision, and what is the 1 minus that would be the probability of choosing the other class, which would be an error most probably. Okay, so the idea goal is that you choose the posterior probability in a way, okay, so that the probability of error, okay, for all x gets minimized. So that means for every x, I need to decide on a class in such a way that probability error given x, okay, gets minimized. So rather, probability of error given x will be minimum of probability of omega 1 given x, comma omega 2 given x. Okay. So the probability that you choose, okay, will be the higher of these two probabilities, and the minimum value of that will contribute to the probability of error. Okay. So now, if you want the probability of error given x and you try to accumulate that over all x, so probability of error comma x dx minus infinity to infinity. So since I'm continuing a continuous PDF and the range of values of x are from minus infinity to infinity, okay, so I can write probability of error comma x dx minus infinity to infinity, which is nothing but the marginalization, which is equal to integral minus infinity to infinity probability of error given x p of x dx. So the idea is to choose the probability, posterior probability, in a way that the probability of error for every x gets minimized. Okay. So rather, we want to make a decision so that probability of error given x is as small as possible for every x. Okay. And we will show that the Bayesian classifier scheme, okay, that we are discussing
Hello, sir.
Yeah, are you able to hear?
Yes, sir.
Yes,
Okay,
sir.
okay, fine. Thank you. Yeah, so what I was saying is that we are trying to actually have states of nature or C classes in general, okay? And you are actually having an unknown pattern, okay? And you are going to construct a d-dimensional feature vector. So whatever I've discussed so far is only one-dimensional feature vector is what I covered so far. But in general, you can derive D features from a object, right? So you can represent them by a d-dimensional feature vector, and you just use the base rule as before, okay? So you come to consider the likelihood, multiply with the prior and divide by the evidence, okay, to give you the posterior probability. So you will get posterior probabilities for each of the C classes, okay? And you assign the pattern to the class that has the maximum posterior probability, okay? So this is the basic idea. I will consider P of omega j given X, and then I will take the maximum value of P of omega j given X, okay, and I will maximize it and choose that index, okay, that value of j for which P of omega j given X is the maximum. So it so turns out that this denominator P of X is the same for all the terms, okay, so that we can directly write probability of omega j given X is proportional, okay, rather than equal to, because P of X is the same for all. It is proportional to P of X given omega j, probability of omega j. That is likelihood times prior is proportional to posterior. Okay. Now, so far what I have done is I've considered a case of what is known as a 0-1 loss function. Okay. So in general, right, when we design a Bayesian classifier, okay, we talk about risks. Okay. So what is a risk? Okay. If you're going to take any action, okay, or if you're going to take any classification for that matter, okay, so there is going to be a penalty added if you make a wrong choice. Okay. So let me assume that lambda alpha I given omega j is the loss incurred for taking action alpha I, or rather choosing omega I class, where the actual class or state of nature is omega j. Okay. So I hope this is clear. So that means we have predicted omega 1, okay, which is the action alpha 1, alpha I, but the state of nature is some other class, which is omega j. Okay. So what we would do is we can compute what is known as the expected loss, okay, by using this formula. Okay. We weigh the losses by their prior probabilities. So lambda alpha I given omega j, probability of omega j, j equal to 1 to c is the risk, and which is nothing but the expected loss. And if you condition the risk for every value of the training data, so that's known as a conditioned risk, R of alpha I given X, is summation j equal to 1 to c, lambda, which is the loss incurred in choosing action I or omega I class given omega j is the true value of the class times probability omega j given X. Okay. And then we can actually try to strive to take the decision in a way so that the overall risk R alpha, okay, for a given action gets minimized. Okay. Or rather R of alpha X given X, okay, where alpha of X is the action that you're taking for a particular value of X, okay, gets minimized for all X. Okay. So this is what is known as the risk minimization principle, and sometimes we modify the Bayesian decision theory by using this risk minimization criteria. Okay. So just for reading purpose, since many of you are there, so you can refer to this book, Duda, Hart and Stock, on pattern classification. And whatever I've covered right now is from section 2.1 and 2.2. Okay. So are there any questions so far so that we can discuss now before we move to the next set of slides? Any questions you have? Can we proceed? Hello?
Sir?
Yes, any question?
Yes, sir.
Yeah, so please ask. Okay, let me see the chat box.
Sir, how to find underlying probability distribution of data set?
Yeah, so this underlying probability distribution of data set, as I told you, all is something like, see, it is like, you know, I want to find out the histogram of the marks of a class. How do we do the histogram of the marks of the class? Let's assume. Okay, I will take the marks of all the students. Okay, I will divide them into some intervals. I will plot a bar plot, okay, or something like that. Now, if I do that for many samples, okay, I will get a continuous curve. Okay, that is many means many. Like in theory, it is infinite number of samples. Okay, I will get a curve. Okay, so that is the way the distribution is plotted. So essentially, the distribution is something like a histogram, you can say. Okay, let me give you an example. Supposing I want to identify, okay, the height. Okay, let us say I want to do gender classification. Okay, male and female. Okay, of the Indian race. Okay, so we know that. Okay, that we know what is the average height of Indian male. We know what is the average height of an Indian female. Okay, so how do you get this average height and the standard deviation? That is because there's an underlying distribution defined for these two classes. Okay, and how is that obtained? You take samples of the given class, make measurements. Okay, you consider it as a histogram. You take enough of samples so that the histogram can be approximated by a continuous curve, and then you define the distribution. Is it clear? Hello? Is it clear or no?
Yes, sir.
Okay, all right. So what I'm trying to say is the distribution is obtained from the training samples of the given class. That is important. Okay? Fine. So, okay, so now we will move on to, I think the slide is visible, the next set of slides. So what we are going to do today is, again, we will continue this risk minimization framework. Okay, I want to in particular talk about a two category classification, okay, wherein the loss incurred in choosing omega I class, okay, when the true class is omega j is lambda alpha I given omega j. Okay, so now please remember that the loss incurred will come into picture only if there is a misclassification. Okay, that is, the classifier decides on something, but the actual class is something else. Okay, so rather if lambda 11 and lambda 22, they both will have zero loss. Okay, because why? Because there will do, so if the classifier decides on omega 1, when the actual true state nature is omega 1, and rather if the classifier decides on omega 2, when the true state of nature is omega 2, okay, there is no loss, okay, incurred at all. Okay, because the correct classification is done. So only when there is an incorrect classification, okay, there only a loss term should be incurred, or should be incurred. Okay, so typically lambda 11 and lambda 22 will be 0. Okay, but let us say that to have a more generic framework, let us just keep them into the term. So I compute R of alpha 1 given x and R of alpha 2 given x, where alpha 1 is the risk, okay, of choosing class omega 1, and alpha 2 is the risk involved, okay, in choosing class omega 2. Now, what I can do is, a rule is the following: R of alpha 1 given x is less than alpha 2 given x. Okay, if that is the case, you choose omega 1. Okay, you choose omega 1 when the risk associated with alpha 1 action is less than that of alpha 2 action. Okay, or rather you can go back and substitute the value of R alpha 1 given x and R alpha 2 given x, and you'll get a relationship something like this. Okay, so you can further write in this form. I know there is a lot of mathematics, but I'm going to skip the mathematics quite a bit, but I'm just going to give you the basic ideas today. Okay, so what does this say? This says that you compute. So what is this? This is the likelihood of omega 1. This is the likelihood of the feature vector belonging to omega 2. So this left-hand side is a ratio of two likelihoods. Okay, and we call this as a likelihood ratio. Okay, we call this as likelihood ratio. And we say that if the likelihood ratio is greater than the right side quantity, okay, then we assign the class X, the sample X to class omega 1. Otherwise, we assign the class X to sample omega 2. Now, one thing to remember here is that the right-hand side, all these parameters are known to us because we know the loss of misclassification. We know the loss of correct classification, which is mostly 0 in most of the cases, because you will not penalize the classifier for making a correct decision. And the priors are known to us. Okay? Probability of omega 2 and probability of omega 1. Okay. So what is omega 2 and omega 1? To reiterate, these are the probabilities. Omega 1 is, say, one object. Omega 2 is a second object. And our goal is to identify, okay, a method so that you can recognize these two objects. Okay. So whenever the likelihood ratio is greater than a threshold, okay, because all of these are known to me and they're all fixed. Okay, they don't depend upon the value of X per se. So we say that they are all fixed and they can be related to a threshold. So if the likelihood ratio is greater than a threshold, then you decide on omega 1, otherwise decide on omega 2. So essentially, if this all these values to the right, okay, if they can be written by a parameter theta lambda, okay. So what I would say is I'm deciding omega 1 if the likelihood ratio is greater than a threshold. Okay. So what I'm trying to do is the following, right? So there is a value of theta over here, and all values of the likelihood ratio greater than the theta, the category of classification will be omega 1. Okay. And then correct. And then if whenever this likelihood ratio falls below this threshold, okay, all those values of X will be identified as omega 2. Okay, and so on. So that is why you look at this region, it is R1, because in the region R1, we assume that the classifier is going to output label omega 1 for the test data X. And at that point, for those values of X, the likelihood ratio, P of X given omega 1, probability of P of X given 2, that ratio is going to be greater than theta A. Now, if so, that's the same thing that you see even here. Okay. Now, if you consider the region R2, so those values of X, the classifier is going to recognize it as omega 2. Okay, and you see that the log likelihood, the likelihood ratio is going to be less than theta A. Okay. Now, depending upon these loss functions, depending upon these loss values, and depending upon the prior, okay, this threshold can vary. So, for instance, right? So this threshold actually varies to another point. Okay, if I choose a different setting for the loss as well as for the priors. Okay. So finally, what are we saying? If the likelihood ratio exceeds a threshold value, which is independent of the input vector X, okay, then we can take optimal actions. So please remember that the likelihood ratio will contain the vector X, and the right-hand side will contain, okay, all the prior parameters such as losses, the prior probabilities, and so on, which are known in advance, so that you will get a threshold. Okay, so somebody has asked a question, so let me just see that. Okay, how to find? Okay, how to find P of X1 given omega 1 when X is a continuous feature? Okay, so you just go to the probability density function and then take the reader value. That's all. Okay, so I think probably I have to switch the slide to the earlier one. Let me just check. Is the slide visible? Prior probability and all that. Hello?
Yes, sir, it's visible, sir.
Is it visible? Okay, okay. So let me just address the doubt it has come. So let me just see. Here, right? So let's say X1 is some value. Okay, if I want to read out probability of X1 given omega 1, there's nothing but the probability density okay, then this will be the value. Okay. Now let's say this, I want to read out probability of x given omega 2 for some x. Okay, then this will be the value. Okay, for a given x. So you just look at the x value. Okay, and you just go to the respective PDF, whether it is omega 1 or omega 2, and read the value directly from there. Okay. So I hope my doubt is cleared. Somebody asked the doubt. Let me check. Oh, okay. I think it's clear. Okay. Fine. All right. Okay. So now let me just continue further. So as I said, we were talking about the likelihood ratio. The likelihood ratio is greater than the threshold. Then you can choose omega 1. Otherwise, you choose omega 2. Okay. So now, so typically we use what is known as 0-1 loss function. Okay. So that means for correct classification, there is no loss. And whenever the misclassification occurs, okay, there is a constant loss, which is 1. Okay. So let us just see that. So what we are trying to say is lambda alpha I given omega j is 0, I is equal to j. Again, I would like to repeat, omega 1 and omega 2 are two objects. Okay. Or omega and omega j are two objects for which you want to identify. Okay. So let us say apples and oranges, or whether you want to identify two human faces, two different persons, you want to identify two different fingerprints, okay? Or you want to identify, you understand, right? So you're taking a pair of objects and you want to do object classification. So please bear that in mind. So supposing if you have seen such objects, R of alpha I given x would be lambda alpha I given omega j, probability of omega j given x. So this is known to you as the expected loss or the risk, okay, which is the risk. And so now, what we are saying, but I is not equal to j, then you lambda alpha I given omega j is 1. For I equal to j, it is 0. So that means for all values of I not equal to j, it is equal to 1. And for the value of I equal to j, it becomes 0. So this boils down to this one. Okay. So all j not equal to I, summation probability of omega j given x. And what is this by definition? This is the 1 minus probability of omega 1 given x. So now if I want to minimize this risk, okay, if I want to minimize the risk, I will have to actually minimize this quantity, or rather maximize probability of omega 1 given x. And that is what exactly we started also with, right? We said that we choose the class whose posterior probability is the greatest. So please remember that assumption that we are choosing the class with the maximum posterior probability, that holds good, okay? That holds good only under the 0-1 loss function, okay? Because only under the 0-1 loss function, okay, do we actually assume that, or do we actually derive that you make decisions, okay, based on probability, maximum probability, posterior probabilities, essentially, okay? So as I said, minimizing the risk requires that you need to maximize probability of omega I given x. So for minimum error rate, I'll have to decide omega I, if probability of omega I given x is the greatest amongst all, greater than probability of omega j given x. Okay. So I think it is clear so far. Okay. If you have any doubts, you can ask. So what have we covered so far? We have covered how to do the Bayesian decision-making process. We have said that relying on the priors is not a good idea always. So you rely on features, and from the features, you can assign a class conditional density, okay? And you take the value of the class conditional density, which is known as the likelihood, multiply the likelihood for a given x into the prior, that is proportional to the posterior probability. And if you're going to assume a 0-1 loss function, okay, choosing the class with the maximum posterior probability, okay, minimizes the risk. Okay. Now, one question is, what happens if you don't have a 0-1 loss function? Then you need to actually go back to here, right? You need to go back here, and you need to actually do the over here, substitute the value of R alpha y given X, R alpha 2 given X, okay? And then you have to see whichever risk is the minimum, and you have to assign that to the class, okay? So at that point of time, you cannot just take the maximum posterior probability, okay? If it is not 0, 1, loss, okay? So that is something important that you need to know. Okay. So the next, so moving ahead, so are there any doubts, further any doubts so far? Because we are doing set of slides one after the other. So if you have any doubts, you can ask me. We are almost finishing 1 hour of the lecture. So feel free and ask some questions. Okay.
Participants, please, if you have any queries, please post it in the chat box.
Okay. So let me proceed on. Okay, if there are no questions. All right. So in this part, okay, for the next 1 hour, I'm going to talk about a discriminant function, normal distribution, and how to get the error analysis for a Bayesian classifier, okay, which is very important. Okay. And then I'll also give you some idea of maximum likelihood if time permits. Okay. But whatever I've covered so far, okay, that is the basic principle of any classifier which is generative in nature. You always choose that class whose probability is maximum. See, even in a deep neural network, right, you choose that class whose discriminant function, okay, or is maximum, okay. So the same idea holds good there also, okay. In fact, in a neural network, you can use methods like softmax function or sigmoid functions to convert the output layer values into probability measures, and that you'll compare against the target values and learn the weights. Okay, at the time of testing, okay, you will use a softmax function to convert two probabilities, and whichever class gives the highest probability, okay, you will assign the sample to that class. So all those principles, okay, they are very powerful, and they have all come into play only because of this theory, which is the Bayesian decision theory. Okay, so that's why this is a very, very important topic. Okay, and it is the basic founding stone, okay, of all the principles, okay, related to.
Please write on a chat box, sir, please.
What happened? No, but hello. They're asking my name. Should I just type in?
Yes, sir.
Hello.
Sir,
Okay. Yeah, I think somebody has typed already. Okay. Fine. Where was I? Yeah. So what I was trying to tell you is that in the section when you talk about neural networks, see, I'm just going through different areas. Okay. If some of you know, right? You have this output layer and you have the softmax layer at the output, which will convert your scores to a probability measure. And finally, the classification, object classification or recognition is done by that score, or you assign it to that class that is the maximum. Now, this idea of this maximum posterior probability, in fact, comes from there. Okay, or rather, this has led to that. So please remember that we are looking at the basics, because everywhere there's a probabilistic interpretation. Okay, so now let me talk about this discriminant functions, okay, which is exactly what is done even in a neural network, how they are getting connected. Okay, so let us look at a multi-category case. So I will design a set of discriminant functions, okay? D1 of x, D2 of x, D2 of x. as many discriminant functions as the number of classes. So GC of X. And I would say that I'm going to assign a classifier to a feature vector, okay, to a particular class, such that GI of X is greater than GJ of X for all j equal to I. So j not equal to I. So what does this mean? This means that I would have C discriminant functions, and I'm going to pick that discriminant functions. Okay. So I would have C discriminant functions, and I will pick that discriminant function, which is the maximum. Okay. And assign that sample to that class. Okay. All right. So what are the possibilities here? So this is something like a neural network. Okay. I have an input layer, and you would have some set of hidden layers and things like that here. But finally, you'll have some set of discriminant functions for each of the nodes in the output layer, G1 of X, G2 of X, and GC of X. You can assign even some penalty terms here if required. And finally, you are going to choose the maximum, and that is the classification that you are going to consider. So in our context, what we will do, we will check up some functions that you can use for discriminant functions. So one way is the maximum posterior probability I can take directly, or I know that the maximum posterior probability is nothing but the product of the prior and the likelihood. So P of X given omega I, probability of omega I. I can also take the logarithm of these two. Okay, so logarithm of P of X given omega I plus logarithm of P of omega I. Okay, so product, right? If you take a product and if you take the logarithm of the product, they become sum, right? Logarithm of P of X given omega I plus logarithm of P of omega I. So these are all possibilities of the discriminant functions that you evaluate here. Okay, and you pick up the maximum value of the discriminant function for recognition. Okay, or rather, I can even consider minus of R of alpha given X. That means minimizing the risk is equivalent to maximizing the negative of the risk. Okay. Okay. So that means if you have any function X and if you want to maximize X, that's the same thing as minimizing minus of X. Okay. All right. So, okay. Now there are some properties of the discriminant functions that are useful. One is that you can scale them for the same constant K, and the discriminant function decision will not change. Okay, because so it is like this. If you have GI of X, and I'm scaling all those GI of X's for the C classes by a factor of K, right? And if I pick up the maximum value also will be scaled by K, but yet the maximum value will be, say, retain the same. Okay, so that's why I mean by saying that discriminant functions do not change the decision when scaled by some constant, positive constant imported by K. Also, if you add a constant to all the discriminant functions, so that is nothing but adding a bias term or an offset. And if you're going to add the same offset for all or the same constant for all, the decision is not going to be affected. Okay. So what are we saying now? We are saying that you have a feature space, and the feature space is divided into C regions corresponding to C classes. And if X is going to belong to Ri, where is the region where X gets assigned to omega I would require GI of X will be the maximum of that. Okay. So of all the discriminant functions, GI of X is the maximum. See this notation, GI of X greater than GJ of X for all j not equal to I, explicitly says that you choose that discriminant function, okay, which is maximum, which is the ith discriminant function. GI of X is maximum in this case. Okay. All right. So we will take some special case known as a dichotomizer, where you have two discriminant functions, G1 of X and G2 of X, and I take the subtraction of both, so that I can now say that decide omega 1 if G1 of X is greater than G2 of X, or rather G of X is greater than 0, and decide omega 2 if g of x is less than 0, okay, which is g1 of x is less than g2 of x. So as before, I can consider even the taking the log of the posterior probability. Why is that we consider the log also into picture? You should remember that the logarithm is a monotonically increasing function. Okay, so that for increasing x, it also increases monotonically. Okay, so that is the reason. Okay, and many a times when we talk about certain distributions, okay, such as Gaussian distribution or exponential distribution, you have this exponential term sitting there, like e to the power of minus x squared or e to the power of minus x term, okay, sitting in term when you talk about distribution. So when you take the logarithm of the exponential function, okay, it makes your job easier. Okay, so that is the main idea. The other way we can consider is that p of omega 1 given x minus p of omega 2 given x. This is the dichotomizer. So you substitute the value of p omega 1 given x, take the logarithm of that, okay, and then you get the relationship something like this. Okay. All right. So now I want to move on to the Gaussian distribution. So far, whatever I've covered, we have covered about the simple base decision theory, that you have to choose the maximum posteriori, and we talked about how to incorporate losses into our formulation, and then we talked about discriminant functions, how to generate discriminant functions using Bayesian decision theory, and you have to choose that class whose discriminant function is the maximum. Okay, so now I would like to just cover what is known as the Gaussian distribution or normal distribution, because this is one of the distribution that is very popularly used in machine learning. Okay, and so it is a form which is like a bell shaped, and it has a mean vector. So let me zoom this a bit for better clarity. There is a mean vector. So this is centered around the mean 0, but in general, you can have mu, which is the mean, and there is a spread. Okay, the spread is denoted by sigma square, which is the variance, or the square root of the variance, which is the standard deviation. So what you're seeing here is a normal distribution with mean 0 and standard deviation as 1. Okay, all right. So the normal distribution has a form p of x. So this is nothing but if you're going to condition for a given class, this will become p of x given omega 1. Okay, so 1 by root 2 pi sigma squared to the power of half is nothing but sigma e to the power of minus half x minus mu by sigma the whole squared. Okay, so, and as I said, if a random variable x follows a normal distribution, we know that the area under the normal distribution should be equal to 1, because it's a probability density function. And also, yeah, the probability that any value x, okay, any feature x will fall in this interval a and b is integral a to b p of x dx. I hope that some of you would have done some course on probability. If not, you may have to brush up on that, okay, to understand these concepts. But if you know what is probability density, the integral of the probability density over an interval gives you the probability measure. So integral of a to b p of x dx. And we can talk about the expectation of the mean value as integral minus infinity to infinity x px dx, and the variance, which is nothing but the scatter minus infinity to infinity x minus mu the whole square, which is the spread or the scatter or the difference of x from deviation of x from the mu px dx. Okay, this is related by sigma squared. So the normal density in pattern recognition or computer vision in general, okay, it is very popularly used. Okay, so for example, in video processing, okay, for segmentation they use GMM, okay, Gaussian mixture models, okay, or k-means clustering. Okay, all of them are related. Okay, so if you consider the normal density, the advantages is that it is tractable and continuous, and a lot of processes are Gaussian in nature. And also, all of you know that if you have a noise sample, if you want to model the noise sample by a distribution, you do that by a normal density, right? Or a Gaussian density, because the idea of that comes from the central limit theorem, which states that if you have large number of independent perturbations or disturbances, okay, and in the limit of the sum reaching infinity, where large number approaching infinity, the resulting distribution will be a Gaussian variable, okay, Gaussian random variable or a Gaussian distribution. And typically all examples of processes which are corrupted by random noise are speech, sounds, handwritten characters, okay, noisy images, okay, and so on. All right. Okay. Now, this is the idea of a multivariate Gaussian distribution, because as I said, we are going to deal with d-dimensional feature vectors, and we're going to assume that the d-dimensional feature vector x is going to come from a distribution which we know is a class conditional density. So if you're going to assume that the distribution in a multidimensional space is a Gaussian, then the equation of the Gaussian PDF is given by this. I'm not going to go into details of this, because I'm not sure how many of you have seen this, but this is very important, okay? Because we assume that the data resides in a high dimensional space typically, and then in that high dimensional space, we want to model a density, and the convenient model that we can use for building a Bayesian distribution classifier is that of a Gaussian distribution. So in that context, I'm presenting you the Gaussian distribution here. It is okay if you don't follow some of these concepts, but anyways, just for completion, X is my input test vector or my feature vector. Mu is a d-dimensional vector, which is known as the mean vector, okay? And sigma is a d by d variance covariance matrix, okay? And so this modulus of sigma to the power of half. So this is nothing but determinant of sigma, okay? So determinant of sigma. So you take the sigma, which is a matrix d by d, compute its determinant, take the square root of the determinant. Okay? So the covariance matrix is a square matrix. The diagonal elements will contain the variances of the individual features, okay? And the off-diagonal elements would give what is known as covariance, okay? Or the cross variance between pairs of features. And remember that sigma 1, 2 is same as sigma 2, 1. So it's a kind of a symmetric matrix, because sigma ij is expectation of xi minus mu I, xj minus mu j. So even if you swap xj minus mu j here and xi minus mu I, it becomes sigma j. So that means any sigma ij is same as sigma ji. So that means to say that this matrix will be a symmetric matrix, okay? So there are also other properties of this matrix, okay? It is also known as a positive semi-definite matrix, because if you take its eigenvalues and eigenvectors, the eigenvectors will be orthogonal, and the eigenvalues will always be greater than equal to 0, okay? So this is a very, very important relation, and many of the concepts, okay, rely on the covariance structure of the covariance matrix. So I'm not sure many of you who have attended my previous lecture on PCA, okay, we talked about covariance matrix. So this is exactly the covariance matrix that we were talking about, okay? So you have a square matrix with the variances and the cross variances, okay? And it is a symmetric matrix. It's a positive semi-definite matrix. So that means the eigenvalues will be positive, greater than or equal to 0. Eigenvectors will be orthogonal, and so on. All right. Okay. So as I said, the covariance matrix is a diagonal elements in the variances of the variables or the features. Cross-diagonal elements are the covariances of a pair of variables or pair of features. And what does statistical independence mean? It means that the covariance matrix is diagonal, okay, which means only the variances exist, and the cross of diagonal terms corresponding to the covariances or the cross variances, they all are zeroed out, okay. Okay, so as I said, the eigenvalues of sigma are non-negative, okay, and the sigma matrix is a positive semi-definite matrix, and so on, okay. All right, so a 2D Gaussian will appear something like this, okay. It will appear like a dome, and there will be a spread in two directions, unlike, so there will be two sets of variances, one along the x direction, other one along the y direction. So essentially it will be like this. It will be like a set of ellipsoids, okay, with a major axis and a minor axis. And then if you look at the number of parameters to estimate the normal density, it is d plus d into d1 plus 1 by 2. The reason why you get d is the d values of the mean vector, which are these, and d into d plus 1 by 2 happens to be because this is a symmetric matrix. So you need d into d plus 1 by 2 parameters. If you are able to get or obtain d to d plus 1 by 2 parameters, okay, you can fill up the other the complete matrix because the matrix is symmetric in nature, okay. So there's also one more thing, this exponential term, x minus mu transpose sigma inverse x minus mu that you see here, there is a name given to that metric. It is known as the Mahalanobis distance, okay. So do you have any doubts so far? Can we proceed? Any doubts?
Participants, please respond if you have any queries. Please post it in the chat.
See, all of you know, I hope all of you know what a normal distribution is, right? In 1D. So whatever I've covered now is a d-dimensional normal distribution, because typically if you have data which is in d dimensions, okay, assuming there is no independence between the data variables, then we actually model it by a normal distribution typically, okay. But if you are assuming independence, then you can write the d-dimensional distribution as a product of the individual distributions in each of the features, and that can be any distribution of your liking. But typically the normal distribution is used, okay, in computer vision applications like Gaussian mixture models, okay, k-means clustering, which is a variant of the Gaussian mixture model, okay, Parsons window, okay, mean shift clustering, okay, everywhere you're going to use a variant of the Gaussian distribution function. So that's the reason why I wanted to introduce you to a multidimensional case. I may probably could have skipped it, but I thought of doing it because at least, even if you didn't understand, right, you're at least familiar with, okay, at least you've been introduced to something like this, right? Multivariate Gaussian distribution and so on. By the way, all of these are standard, okay, there is nothing very new about these things. They're all well explored, well explored distributions. Okay, you can just refer to Duda, Hart and Stop, the book I was mentioning to you about. Okay, you can just refer to chapter 2, and all this material is there in chapter 2, whatever I'm covering now. Okay. Okay, so any doubts so far? Because these are the last set of slides which I have, and then I'll just give you an idea of how we can extend the Bayesian decision theory. Okay, other methods, I'll just spend some 10-15 minutes on that, and then we can take up some questions and answers, because I want some interaction from the participants, right? I mean, you cannot talk about something which is related to your work, we can discuss. If some of you research scholars, some of the things which you have seen here, right? I mean, they're not something very new, right? I mean, it's a different thing if you're not aware of it, that's okay. But you please ask some questions, okay? Because that's the focus of these workshops. You can ask some questions on how it is used. I'll be able to help you out. So can we proceed?
Yes, sir.
Okay. So I'll give some time for questions in the end, at least 10 minutes before winding up. Okay. Okay. Now, as I told you, okay, in the beginning of the lecture, we said that the Bayesian decision theory, okay, we are going to do error minimization over there. Okay, so I think the question has come. So let me just see it. Okay, nothing has come. Okay, fine. Yeah, so so in the beginning of the lecture, okay, an hour back, I talked about whenever you're going to make a decision, I'm going to choose a decision so that my overall error, okay, across all the feature samples possible, okay, is going to be as low as possible, right? So how low can we get? Okay, how low can you bring down the error? Okay, so that is the question we are going to ask now. So see, the way the errors get contributed, they are as follows, right? So if for a two-class problem, I can assume that X belongs to R1. So that means that this is the classifier decision. Okay, so this is the classifier. X belonging to R1 means the classifier is going to assign X to omega 1, but the actual class is omega 2. Or the other possibility is X belonging to R2, comma omega 1. So that means classifier decides on omega 2, actual class is omega 1. So this is the same thing as probability of X belonging to R1 given omega 2, probability of omega 2. These are all probabilities plus integral plus probability of X belonging to R2 given omega 1, probability of omega 1. And this we know that if given a density, if you integrate the density, you will get the value of the probability. So probability of X belonging to R1 given omega 2 is the same thing as integrating the density probability of X given omega R2 over R1, over the region R1 times P of omega 2 plus, okay, probability of X belonging to R2 given omega 1 is nothing but taking the class conditional density of P of X given omega 1 and integrating that over R2, okay, and multiplying with P of omega 1. So let me look at this figure, okay. So I'm plotting P of X given omega 2, probability of omega 2, probability of X given omega 1, probability of omega 1, okay. So that is the plot which you are seeing here. So this is nothing but probability of X given omega 1, P of omega 1. This is nothing but this plot, okay, which you see here. Please see this plot. Is probability of X given omega 2, probability of omega 2, okay. And this plot that you are seeing here is probability of X given omega j, probability of omega j, okay. So not probability, is the probability density. Sorry, it's the probability density. So now, if I integrate, okay, this, if I shade this region that is shaded, right, that is nothing but the integration of this curve, essentially, okay. So now, if you consider, okay, having a decision over here, right, if you consider a decision over here, then what are the regions that can go misclassified? So that means to say, if I'm going to consider the maximum posterior probability measure, so for a training sample here, okay, so which class will it get assigned to? it will be assigned to omega 2. So that means it is R2. So that means all samples, okay, greater than X star get assigned to R2. All samples less than X star get assigned to R1. But let me assume that I'm considering Xn now. Okay. So that all samples less than Xn will be assigned to R1, and all samples greater than Xn gets assigned to R2. So in that case, my probability of error would be this curve and this curve. Okay, it will be this and this, because why I'm saying that is, so let's say that if I take this point, okay, you're going to choose the maximum probability, okay, or the posterior probability. So I'm going to assign to omega 1. But let us say that this point actually belongs to omega 2. Okay, so that means it gets misclassified. Similarly, if you consider a point here, it's going to get assigned to omega 2, but the actual class was, let's say, from omega 1. So be very careful. I will take this curve and all these regions, okay, please see here, all these regions, they will get misclassified if I'm considering omega 2 curve, because they will get assigned to omega 1. Okay. Similarly, if I take this curve omega 1 and if I consider this shaded region, all the samples will get misclassified because they will get assigned to omega 2. So the actual class was omega 1, they get assigned to omega 2. So there is an error. So what is the total error now? The total error would be nothing but this shaded region and this shaded region. Now the question is, what happens if you move this decision boundary or this xn to some xn x star? So you will see that there is this region over here, okay, which also will start contributing to the error, because this region actually belongs to omega 2, but your classifier would say that it belongs to omega 1, because less than x star means it is R1. Okay. So there is this particular error, which extra error that comes in, but it can be reduced. Okay, it can be reduced. So what are we trying to say? If you choose, okay, the class whose maximum posterior is, whose posterior probability is the greatest or maximum, okay, you will achieve, okay, the lowest error rate. Now, the error rate will not be equal to 0. Okay, the error rate will become to 0 only if these two distributions or if these two curves do not overlap. Only then the error rate can be equal to 0. Okay, but otherwise there will be some error that you will have to tolerate, but you will make a decision so that the error rate is as low as possible. Okay. Okay, so this is for a C2 class problem. Now, in general, if you have multiple classes, say C classes, I will have to find out the probability of correct decision, which is the probability of X belonging to Ri, wherein the classifier assigns to omega I and actual class is omega I. So over all possibilities I equal to 1 to C, which will be I equal to 1 to C, probability of X belonging to Ri given omega I, probability of omega I. So like before, this probability is the integration of over Ri, probability of X, probability density of X given omega I, probability of omega I equal to 1 to C. Now, the reason why we do this in this formulation is that when you have multiple classes, you cannot find the error rates, because a particular sample, a particular class can be having an error with some other classes. So you have multiple pairs of classes that can go in misclassification. Okay, like for example, if I have omega 1, right, probably it can go to omega 2, it can go to omega 3, it can go to omega 4, assuming there are 4 classes. Similarly, omega 2 can go wrong with omega 3 and omega 4. Okay, and omega 3 can go wrong with omega 1 and omega 2 and omega 4. Okay, so there are multiple classes, the pairs of classes for which the for which errors can happen. So that is the reason. Okay, that is the reason why we consider the probability of correct decision and take the 1 minus of that to get the probability of error. Okay. Okay. Now, the last topic, okay, is so far I've assumed that we have continuous features. So there are applications where I can use discrete features. And whenever you have a discrete features, I'm assuming that the components, the feature vectors are integer valued. They are not continuous in nature. So that actually they can be either binary or integer valued. So that my class conditional density becomes a conditional probability mass function kind of thing. So something like probability of x given omega j, probability of omega j, probability of x. Same idea. The only difference is that you no longer have a PDF, but rather you have a probability mass function. So same principle as before. You have to consider the risk and you have to take that action that will minimize the overall risk. Okay. So I would like to give you an example now that if you have a binary feature which are independent, okay, and you have two categories. Let us assume that you have data which is in d dimensions, and each of the binary features, okay, features are binary in nature, where each xi is either 0 or 1. So for a given class, there are two classes, probability of xi equal to 1 given omega 1 is pi, and probability of xi equal to 1 given omega 2, the second class is qi. Okay, so that means probability of xi equal to 0 given omega n will be 1 minus pi, and probability of xi equal to 1 given omega 2, right, will be equal to 1 minus qi. Okay, so you can go and write down the assuming conditional density of the components of a feature vector. You can compute the likelihoods like this as follows, and then you can compute the likelihood ratio. Okay, and then you can get the discriminant function. Okay, you can get the discriminant function, and finally you can make the decision. Okay, so this is just to give you an idea, okay, of how to work it out. All right, so what have we covered so far? We have covered about Bayesian decision theory. We have talked about how to choose the maximum posterior probability, and we choose the maximum posterior probability and the 0-1 loss function. And whenever you have cases where misclassifications are going to be penalized, okay, differently, then you consider selecting that class that gives the minimum risk. Okay, and then we moved on to discriminant functions, and then I talked about if you have d-dimensional data, I introduced to you the multivariate normal distribution of the Gaussian density, wherein I talked about the mean vector, the covariance matrix, properties of the covariance matrix briefly. And then we talked about how to compute the probability of error. And we said that you need to choose always the maximum probability, maximum posterior probability under the 0-1 loss function, okay, so that the probability of error will be minimized. And lastly, we talked about discrete random variables or discrete features, where instead of the class conditional density, we incorporate or make use of probability mass functions and then develop the Bayesian decision theory. So some of the last slides before we get into the discussion mode, okay, is how do you evaluate the classifier? So typically, as I said, you would have something known as a true positive, assuming this to be a positive class and this to be the negative class. So that means the correct classification has happened to the correct class. And then what is true negative or correct rejection? It means that the class is negative and the decision made is also negative. Now the question is, what is this false positive and false negative? So false positive means that the class is negative, but it gets assigned to positive. Okay, so it is like, for example, if a person is healthy and a person is non-healthy, a non-healthy person, a person is non-healthy, that is the positive class, and let's say a person is healthy is a negative class. So if a person who's healthy becomes declared as non-healthy, that's a false positive, or vice versa. Okay, so the other one is false negative or miss, where actually the true anything which is positive has been declared as negative. Okay, so these are so what are two types of errors now? The two types of errors are false positive and false negative, and the two types of positive samples are true positive or true negative, wherein your classes are correctly classified. Okay, if it's a positive class, you also get a positive value. If it's a negative class, the classifier also says it's a negative class. Okay, so the confusions occur or the errors occur when a class which is positive gets declared as negative, or a sample that belongs to a negative class gets declared as positive. Okay, all right. Okay, whenever you develop a classifier, once you want to evaluate its efficacy, then we actually talk about what is known as a ROC curve, that is the receiver operating characteristics. Okay, and they are very much used in computer vision applications. They are also known as area under the curve. Okay, these are all metrics that are used in computer vision and even video processing. So what we try to do here is to give you an example. I have given you two Gaussian distributions with the mean of mu1 and mu2. And let's assume that for the discussion, their spread is constant, this sigma. I'm going to define what is called as a discriminability ratio between the two distributions. Now, obviously, this ratio will be good if it is high. So rather, the mu2 gets separated from mu1 by a very vast distance, then the discriminability would be better. Okay, so now what do? We consider different values of d. Okay, we consider different values of d, and then so that your mu2 and mu, so the placing of the distributions become fixed once d is fixed. Okay, because mu2 minus mu1 by sigma. So when d is fixed, that is the relative displacement between mu2 and mu1 by sigma is also fixed. Okay, now I vary the threshold. Okay, keep on. So this is one threshold. Then I vary the threshold to the next value, the next value, the next value, and so on. And I calculate these parameters: false positive, false negative, true positive, and true negative. I choose two of them. So let's say false alarm and hit. So false alarm is false positive and hit. Okay, and for every threshold, I plot a curve for a given value of d. So I get a family of curves now. Okay, so I get a family of curves like this, and they become steeper and steeper, right? As d increases, they become steeper and steeper, approaching a ideal step function. Okay, so the idea is I consider a pair of distribution with discriminability ratio d. Then I vary this threshold x star, which I showed here. I keep on varying this from here till all the way till here. And for every x star, I will get a set of false positive value and a true value, which I plot on a curve, 2D curve, and I get a curve from there. And I essentially, these are nothing but variation of these probabilities, right? For false alarm and the hit. And for a discriminant ratio, which is fixed, they present a smooth curve. And this curve is known as a receiving operating characteristics. Okay. All right. So as far as I am concerned, right, I think I've given you some enough of details on the Bayesian decision making. Only what is left to be done, okay, which I will give you an idea, is how do you estimate the parameters of my distribution. Okay, so I don't want to get into that right now because there is a lack of time, but I would like to just tell you that So let me just stop sharing the slide for a minute. Okay. Yes. So I would like to just tell you that there are methods such as maximum likelihood methods and so on, which are typically used, okay, which are typically used to estimate the parameters of your distribution. Okay. So, and once the parameters of the distribution are estimated, okay, then your class conditional density gets defined, and then you can multiply the class conditional density value, which is likelihood, into the prior to get the posterior probability and make your decision. So let me just give you a very, very brief idea about maximum likelihood estimate. Okay, I'm not expecting you to, but this is a very estimation techniques are very important in computer vision. Okay, so I will just quickly give you an idea of maximum likelihood estimation, and then we can close. Okay. So do you have any doubts so far? Because we have now 10 minutes left. Anybody quickly? Hello? Do you have any doubts?
Participants, please respond.
Because I can always stop here and we can discuss some questions if you have, instead of going to a new topic. Because maximum likelihood, I don't know how many of you will follow, but I will just give you an idea of it in 5 minutes, and then we'll plan to wind up. So if you have any questions right away, we can start discussing. Okay, so let me just continue. So I'm not going to go through these slides in detail, okay, because they are a little bit mathematically involved. But what I would like to say is that when you design a classifier, okay, we will have to estimate the parameters of the class conditional density. And how is that estimation done? That is done from the training data, which is given to you and labeled. Okay. So there are two techniques here. One is the maximum likelihood technique, and the other one is the Bayesian technique or the Bayesian estimation. Typically, the results are nearly identical in both the scenarios, but remember that the approaches are quite different. So in maximum likelihood, we assume that a class conditional density is available. Its form is known to us. So let us assume that the Gaussian distribution is there with some mean vector and covariance matrix. And the question is, how do you get the mean vector? How do you get the covariance matrix? So that is obtained during the training process. Okay, that these are the parameters that you have to learn during the training process. Okay, and for example, I can assume a exponential distribution with some parameter lambda. So what is the parameter that has to be learned? That is lambda. And how do we do that? We do that using two techniques. Either two techniques are fine. One is maximum likelihood, other one is Bayesian estimation. So let me just tell you what is maximum likelihood, just to give you an idea before winding up. So maximum likelihood is a technique, okay, which is which says that, okay, I'm going to observe the probability of obtaining the samples, and I'm going to maximize their likelihood or their probability in a way that they support the parameters are chosen in a way that they best describe the training data. Okay. Contrary to that, the Bayesian learning is going to place a prior on the prior distribution, the parameters themselves, and going to convert this prior to a posterior probability density by observing samples, and then this distribution is going to peak at some point, some parameter in the parameter space, and pick that value. So this is known as map estimation also. Okay. So please at least remember ML estimation, map estimation, even if you didn't understand what I said. These are methods that are used to actually learn.
Allow me.
Yes. Yes. Hello?
What are
Yes,
the-
please ask.
I wanted to ask you that what are the limits
Voice
of
is-
these methods?
What are the limitations? No, your voice is breaking.
Yes,
Can you
sir.
please-
Limitations.
Okay, so one thing you need to remember
Sir.
is that limitations of which method? The maximum likelihood map estimation, that one you're asking? Or which method you're asking?
Yes, sir. Whatever that is maximum estimation method, sir.
Okay, so maximum likelihood
Maximum
estimation depends upon the data. Yeah. So it depends upon the data, and if the data is, like if you choose a wrong model, okay, to begin with, then your estimation will give you a wrong, it will be wrongly estimated. So, for example, if you assume that the data is taken from a Gaussian distribution, but let us say that the actual distribution is Gaussian, is something else. Okay, then what you would do? You would be estimating the parameters of the Gaussian distribution. Correct. But the distribution is not because you have chosen the wrong distribution. Okay. So the maximum likelihood estimation has a limitation that you need to have a priori knowledge of the distribution that you are going to fit parameters on. So that is one thing. And the other thing is that the other thing is that these maximum likelihood methods will fail if the data is quite limited. Okay. Is the doubt clear? Hello? Madam, is the doubt clear? Whoever asked. Okay, so let me just, yeah. So now, yes, what is the accuracy? Okay, so accuracy would be like the correct classification. That's all. Okay, so if you have, let's say, 200 samples, and let's say your classifier predicted 150 samples to be matching with the actual labels, correct labels, then it will be 150 by 200, which is 75%. Okay, so that is how classification accuracy is defined. The other way of doing classification accuracy between pairs of classes, you can generate the what is called the confusion matrix, okay, which is also typically used. So the confusion matrix will say, okay, how many times, okay, did this class get wrong with some other class or get misclassified with some other class? So any doubts? Since we have 10 minutes, we can discuss now. So everybody is clear of maximum likelihood, right? So essentially, you are going to estimate the parameters of your distribution. That's all. And for that, you need to have, you're going to choose the correct model of the distribution so that the parameters will be matched will be matched properly for giving you a good class, for developing a good classifier. So if your model is not correct, right, then your parameters also will not be in sync with the actual data, right? So there you will have a problem. Or if you have very less data, so that is when the prior probabilities, prior distribution also comes into play. So when your data is limited, then the prior density can play a role, okay, which is the map estimation. Okay, so we have another 8 more minutes. So anybody can ask me questions now, because I want it to be an interactive session. I mean, that's all I have to say. I mean, I'm not going to cover maximum likelihood estimation, as I told you, but I'm just giving you an idea as to what it is. Okay, so that, you know, so essentially you are going to assume a distribution, isn't it? So we assume a distribution and we assume that the distribution is parameterized, okay, by a so what are the values, the parameters? Okay, so for example, I'll give you an idea. Suppose I want to measure the degree of color in an orange and in an apple, okay, the degree of redness. So we can say that the distribution of the redness follows a normal distribution. But what is the mean? What is the standard deviation? Okay, so that is estimated by considering samples of oranges, and that is estimated by estimating samples of apples. For every class, you have a class conditional density. The parameters of the class conditional density you are estimating using maximum likelihood estimate or using map estimation and so on. Okay. Okay, so I think I'm done. So anybody else can ask some questions if you have, otherwise we can wind the session. So please remember that this is very, very important. Okay, whatever I've covered so far, because it's used in a lot in object classification. Okay, it's used a lot in computer vision applications. Okay, object recognition, object detection. Okay, I've not talked about features yet. Okay, that will be the next talk. But I wanted to just talk to you about like how to build a classifier for object classification, object detection, and so on. Okay, in a computer vision framework.
There is one question. What is the accuracy?
I've already discussed that. I already told them that it will be the number of correct classifications divided by total number of samples. So if you have 200 samples, 150 of them were classified correctly, then it will be 150 by 200. Okay, so I think if there are no questions, I think you can wind up, or do you have any more questions participants can ask for the next 5 minutes, or otherwise we can wind up.
Participants, please respond. If you have any queries, please post it in the chat box.
Okay, so I think we can wind up then, madam.
Yes, sir. Thank you, sir. Thank
Because
you for your wonderful session. Your session has given us a very good information, and it's very informative, sir, and it's very interactive also. And thank you so much, sir, for teaching us topics which will be helpful to our research.
Just have 4 minutes, so let's say.
Our clarification session also you have explained us very clearly, sir. Thank you, sir. Thank you so much. It is our privilege to have you as a resource person today.
So yes,
Sir, your voice is breaking, sir. It's not clear. Sir, sir,
hello.
sir.
Yeah, there is one question that has come. So let me address that. Okay.
Okay, sir.
Yeah. So it says that if there is a change in the probability distribution over time, so I mean, I'm not clear. What do you mean by change in the probability distribution over time? So generally, your distribution should be fixed. Okay, it should be invariant to time. Okay, it should not vary. Okay, so I cannot answer that question because as far as object, so I mean, see, whatever, even if there is a change in the probability distribution, right? You suddenly the object is not going to move from one place to the other, right? It's still going to be gradual. So in that way, this question may not be that apparent, right? So we are going to assume that whatever distribution you have is going to be invariant over time, okay? Or rather, it's going to be time dependent, independent. Okay, I'm just talking to Varsha's doubt over there. Okay. Okay, so I think we can wind up then.
Yes, sir.
Are you able to listen to me? Hello?
Yes, sir. Yes, sir.
Yeah, you're able to listen, right? Oh, okay. So,
Thank you, sir. Thank you so much, sir.
okay, right. So I'm leaving the meeting then, if there are no doubts. Okay.
Okay, sir.
Okay, thank you all. Okay.